I forgot to recording it again. Okay, it seems being recorded. So from this last equation, you can go back to the context-free grammar like this. So let me change the column. So L arrow AL prime, which is opening parenthesis L prime. And the L prime is B or MB. So closing parenthesis or M closing parenthesis. So this is the result of left factoring. So in your mind, in your brain, you can think about that, and you can just switch it to this grammar. This is called left factoring. I can visit here while doing error parsing. So this is the special form of left factoring. So let me just think about that. But so you can perform it like this, but in your EBNF form, you don't have to do that. So in your EBNF form, so following this, you can do it. Opening parenthesis and list prime, which may be list 1. And list 1 is closing parenthesis or members and closing parenthesis. Okay, so this is a valid EBNF. But in your you can have a more EBNF symbol in the EBNF form. You have an optional form. So I can do that with, rather than this, I can do that with option, which is option members and closing parenthesis. Okay. And in your members, you are repeating plus of S expression. So S expression plus. Actually, in an EBNF form, I have which was introduced in the last lecture. You can do a repetition for this. Brace, stop, and brace plus. And the last one is atom. Atom is either ID or none, which is the token. Okay, so this is an EBNF for LISP syntax. So let me save this. So I can share this if you want to do that, want me to do that. So this is a LISP syntax. But so from this EBNF, you can directly write a recursive distance parser. But in our case, we want to make it using Lex and Yak, so which is a Flex and Bison. So that is the topic of today. Do you have any questions up here? No questions? Then I'll remove all of this, and I'll share the today's handout. So today's laboratory work is symbolic expression, which is just S expression in LISP. So as explained before, LISP adopts the generalized list to represent a list. Since a generalized list may contain a list, you can represent AST. So I mean that generalized list is essentially tree. That is the point. So you can represent an AST using a generalized list. For example, LISP expression plus 1, 2 can be represented by the following structure. Plus is the first element, 1 is the second element, 2 is the third element. So you can just make it a little bit, tweak a little bit. You can find that there's a dot. Left is plus. Another dot. Left is 1. Another dot. Left is 2. And you have nil here. So this is the identical. So with some tag, this is character plus the integer 1, integer 2. So this list, which is generalized list, is essentially a tree. And you can use this tree as an AST. You can use an AST for this, okay? So as you know, we have explained this generalized list. We have implemented it in the last lecture, not the last lecture, but laboratory 5. So we can use it today. So implementing the generalized list lets you use the previous design of the data structure, list and data. So in the data, you have 3 tags: int, character, list, and int for int value, character for character value, and list is a list value. And list is defined as node pointer. So list is struct node pointer. So it can be a null, or it can be a node with a certain value which is containing a data. And next, okay? So 3 constructors for data. So you know that you have 3 tags. So you have 3 constructors: make int, setting the field into val, make a character, setting the field of character val, and make list, setting the field lst val, list val. So you have 3 constructors and 1 constructor for list. Actually, there is 2 constructors, which is nil. List requires 2 constructors, nil and cons. But as you know, we can use null for nil, so it is not used here. But even though this is true, you can make a nil additionally. List cons, data pointer, and list. So it is making internal node with the data and next. Okay, just allocate a node and setting the value field with A and setting the next field with ls. Okay, that is the definition. So if you want to, you can make another constructor which is null. So you can make it as a list of nil accepting nothing. So it just will return null. So in any way, we do not take that thing here. And for more functions, these functions, these functions are accessors. Car means the value part, and CUDA means the list part. So once you have a list of something A and D, if this is your address, if your address is here, car address is A, and CUDA address is D. So you can consider this as a first component of a list, or second, which is not actually second component, but the list part, rest part of it. Did I set this as the where it comes from? Did I set this? Say about that? Said that? Actually, the LISP structure is the application of function to the arguments. So they are thinking about that this is the data part. And actually, in the list term, it is star arguments. And this is the command part. Originally. So they are taking this as a command part, which is, this is a command part. This is a data part. So they are actually in the registers, called registers. So CAR stands for Command Address Register. Command Address Register. And CDR, CUDA, means Command Data Register. So the names comes from that there, but nobody concerns about it. So just use car and CUDA. For C2S is character to string, returning a character pointer, I to string, integer to string, L to string. So these three routines for printing a list. So you can make it or not. You can support it or not. So any questions up here? No questions? Then incorporating with Flex and Bison, so you can have additional fields, which is for integer var and character var. And you need two types. One is data pointer. The other is node pointer. Actually, structure cannot be stored here. So even though data is defined as struct data pointer, struct data, it is not allowed a type definition here. So you will use the original type, struct data pointer, struct node pointer. Actually, this is the list. As you know, this is the list. And this is the data containing a list. And you have two tokens. Number is for integers, name for strings. So you add it as value. And for character, I'm just using the plus sign as an operator, but you may add it further. And dval, data val, is a star symbol, S expression, atom, and list are all data value. Ival is lval, sorry, lval is a list value. It's a members. So your star symbol is a single S expression, and you will set the value, which is data, as a root. So the root is a global variable declared here. So this global variable is set as the result of the AST. And this expression is either list or atom. And for the list case, assign it. Atom case, just assign it. Nothing special. And list, this is the point where it differs from the anti-error grammar, since the members can be empty or a sequence of S expressions. So opening parenthesis, members, closing parenthesis, and make a list is, you know that this is a list value. So this is the list. And you want to save it into data. And you can make a constructor, make a data from a list. So then assign it. And for members, let me just, okay, up to here. For members, if it is empty, you will set as null. These are actually these are the constructors of a list. If it has S expression members, you can make a cons later to the list. So they are using list constructors. And atom number make an integer, data constructor integer. Atom name, actually I'd like to make it as a string, but we do not have a string yet, so it is just extracting the first character. The first character is extracted and make a character, and plus is to make a character as a sign. So for this, you just understand that for this token, you need a value. So we have to set it from LISP input. For your main YY parse and print data, the root returns 0. YY error is use the put string as usual and exceed. And the LISP part, corresponding LISP input, is defined here. std@ib.h is used for a to I for making an integer from a string. So YYLVAL IVAL for numbers, sequence of digits, one or more digits. IVAL is set to a to I from YY text and return none. And sequence of alphabets, the setting, the YY text as SVAL and return name. As you know, there was a tricky error in the last lecture. In order to prevent it, you can make a memory allocation here. So you may make a malloc and string copy and return it and set it. Setting the SVAL. So you can do these combinations here, but they can make a space leak. So I just use copy it and just transfer the needs for the memory allocation to your Bison part. And for plus, return plus here. Okay. So only the YY text will be returned. And opening parenthesis and closing parenthesis. So for this case, you may want to set YYLVAL, the CVAL, character val. So is this character? So let me just pick it about it. CVAL, okay. So CVAL is set as YY text 0. Okay, so you can make it more clearly here. opening parenthesis, closing parenthesis, white spaces are skipped, new line is end of input. Okay? Any questions? So no questions. Let me just show this from your terminal. Let me just make a somewhat big terminal for this. So in your compiler, have 11 questions. Okay, I'll check you 10 yes. So you know that you can do S expression and Y. So it is same to that thing, including YY error. And split. What was it? So let me just check it. Yes. Atom.m. So for this case, I set this. If we return it, set YYL var C var as YY text 0. Okay. For make file, you can find it. There's a make file which is source S expression depending on sources and headers. And you have another source, data.c and data.h is described here. And why the tab.c depends on S expression.y. Why the tab.h is S expression.y. Next, the y by the c is atom.l and with headers. So let me just take a look of data.h. So data.h, this is the definitions which was described here. So I added PR data, which is a print data here. So actually this PR data is used in here, in your Bison input. So you know that in the last Bison input, can you see that there's a PR data here? PR data root, it is used by print data. And data.c is somewhat complex, but you can make it as a cons, calculator, I2S, C2S, LS, LISP2S, PR data, print, list, MK int, MK character, MK list. So they are all implemented here. So in your terminal, you can test it. So in order to make it, let me just touch it. Expression and then make it. So once it is built, you can execute it as expression, and you can make 1, 2, 3, same as before. Okay, so you can see that it is same to just storing a string and printing it. You can think about that, but let's just get the power of lexicon analyzer. 3 atom Okay. So you know that at all is shortened with a single character. Okay, so it is changed as A. So another example, plus 1, 2, which was the example in your handout. So plus is a singleton character and 1, 2. If you want to express it, compiler, and you are implementing it in C. So just the first character of the compiler is extracted. So this is the outline of today's work. Do you have any questions up here? No questions? Okay. And let me go back to the original problem. Using the above skeleton code, write a program reading a generalized list and calculating the area of the list. As you know, the area of the list is the number of atoms in the list and the maximum depth. So it is the product of width and the height. Width is the number of elements in the list, and the height is the depth of the list. The depth of a list is containing only atom is 1. So if you have an atom, you may consider this width is just 1, and height is also 1. So the area should return 1. But if you have a list plus times 2, 3, 5, then you know that the width is counted 1, 2, 3. So width is 3, and the height is 1, 2 rather. So height is 2. So it is, the product is 6. So an atom can be a positive integer, an alphabetic string, or arithmetic operator, one of plus. I just exemplified plus here, but you should extend it minus, times, divided by, slash, and modulo, which is percent. You may define and use other functions as well. Make sure your source code satisfies the following constraints. Type data with functions, integer, and you have to add nkstr for the string argument. Define and use list with 3 functions, cons, car, and CUDA. Define and use the conversion functions, C to S, character to, this should be a character. This should be a character. So character to string, integer to string, and list to string, and Y string to string. It is already string, so you don't need it. If the program submitted does not fulfill the constraint, take no points even if the LISP evaluates it with any non-zero scores. And then, based on the experiment, to make a report with references, assignment 8, you can write a report in Korean. Your report should contain the following materials. The purpose of this report in your words, your Flex and Bison info files, and other source files with explanations. And what you have learned in this laboratory, your program should read from the standard input. The first line of the input contains an S expression in LISP syntax. The program should print the area of the input expression. The following shows some sample input and output. Do you have any questions? No questions? And may all of you be succeeded in making an S expression. Thank you. Thank you for up to now. 수고하셨습니다.